5 Angle modulation and demodulation 5.1s discussed in the previous chapter. A carrier modulation can be achieved by modulating the amplitude frequency and phase of a sinusoidal carrier of frequency JC, and that chapter we focus it on various linear amplitude demodulation systems and their demodulations. Now we discuss nonlinear frequency modulation, FM, and phase modulation, PM, often collectively known as angle modulation. Nonlinear modulation inum signals the amplitude of a Fourier is modulated by a signal t, and hence the information content of t, isn't the amplitude of variation soft carrier. As we have seen, the other two parameters of the carrier sinusoid, namely its frequency and phase, can also be varied in proportion to the message signal as frequency modulated and phase modulated signals respectively. When out ascribe the sense of frequency modulation, FM, and phase modulation, PM. False start. In the 1920s, broadcasting was in its infancy. However, there was an active search for techniques to reduce noise, static, since the noise power is proportional to the modulated signal bandwidth, sidebands. Efforts were focused on finding a modulation scheme that would reduce the bandwidth. More important still, bandwidth reduction also allows more users, and there were rumors of a new method that had been discovered for eliminating sidebands. No sidebands, no bandwidth. The idea of frequency modulation, FM, where the carrier frequency would be varied in proportion to the message t, was quite intriguing. The carrier angular frequency W, t, would be varied with time, so that t equals We plus Km, t, where K is an arbitrary constant. If the amplitude of m, t, is then the maximum and minimum values of the carrier frequency would be We plus Km and Wekmp respectively. Hence the spectral components would remain within this band with a bandwidth 2 km centered at We. The understanding was that controlling the constant parameter can control the modulated signal bandwidth. While is true, there was also the hope that using an arbitrarily K could make the information bandwidth arbitrarily. This possibility was seen as a passport to communing. In heaven. Unfortunately, experimental results how that the underlying reasoning was seriously wrong. The FM bandwidth, as it turned out, is always greater than, at best equal to, 202. 5.1 Non-linear modulation 203 Figure 5.1 cons PTOF instantaneous frequency. THEAM bandwidth. In some cases its bandwidth was several times that of AM. Where was the fallacy in the original reasoning? We shall soon find out. The concept of instantaneous frequency. While AM signals carry a message with their varying amplitude, FM signals can vary the instantaneous frequency in proportion to the modulating signal, t. This means that the carrier frequency is changing continuously every instant. Prima facie this does not make much sense, since to define a frequency we must have a sinusoidal signal at least of your own cycle, or a half cycle or a quarter cycle, with the same frequency. This problem reminds us of our first encounter with the concept of instantaneous velocity in a beginning Chanuk's course. Until the presentation of derivatives via Leibniz and Newton, we were used to thinking of velocity as being constant over an interval, and were incapable of even imagining that velocity could vary at each instant. We never forget, however, the wonder and amazement that was caused by the contemplation of derivative and instantaneous velocity when these concepts were first introduced. A similar experience awaits the reader with respect to instantaneous frequency. Let us consider a generalized sinusoidal signal p, t, given by LTP, t, equals a cos 0, t, 5.1, where 0, t, is the generalized angle and is a function of. Figure 5.1 shows a hypothetical case of 0, t, the generalized angle for a conventional sinusoid a cos, wet plus 80, is a straight line wet plus 80 as shown in Fig. 5.1. A hypothetical case general angle of 0, t, happens to be tangential to the angle, wet plus 80, at some instant. The crucial point is that around over a small interval float 0 the signal p, t, equals a cos 0, t, and the sinusoid A cos, wet plus 80, are identical, that is, LTP, t, equals a cos, wet plus 0 T1 LTT LTT2 where is certainly justified in saying that over the small interval float, the angular frequency of LTP, t, is we because, we t plus 80, is tangential to 0, t, the angular frequency of LTP, t, is the slope of its angle 0, t, over this small interval. We can generalize this concept at every instant and define at the instantaneous frequency we at an instant as the slope of 0, t, att thus, for (204) angle modulat Ianandi modulation LTP, t, in EQ, 5.1, the instantaneous angular frequency and the generalized angle are related via Wi, a, de, 5.2a, 5.2b, de Wt, equals, dt0, t, equals 1, 0, 0. Now we can see the possibility of transmitting the information of m, t, by varying the angle 0 of a carrier. Such techniques of modulation, where the angle of carrier is varied in some manner with a modulating signal m, t, are known as angle modulation or exponential modulation. Two simple possibilities are phase modulation, PM, and frequency modulation, FM. In PM, the angle 0, t, is varied linearly with t, 0, t, equals wet plus 80 plus kpm, t, where pi is a constant and y the carrier frequency. Assuming 800, without loss of generality, 5.3a, their resulting pm wave is 5.3b. Wi, t, equals we plus pm, t, dt. The instantaneous angular frequency wi, t, in this case is given by d0k, 5.3c, hence in pm the instantaneous angular frequency wi varies line arly with the derivative of the modulating signal. If the instantaneous frequency is varied linearly with the modulating signal we have fm. Thus in fm the instantaneous angular frequency is 5.4a, where k is a constant. The angle 0, t, is now 0, t, equals 1, 0, 0 we plus ktm, a, de equals wet plus kt1, 0, 0 m, a, de. Here we have assumed the constant term in 0, t, to be 0 without loss of generality. The FM wave is 5.5. 5. 1 nonlinear modulation 205 figure 5.2 phase and frequency and C modulation are equivalent and interchangeable. M, T, I modulator IPPM, T, I frequency RH, T, M, T, DRIIIIFJM, CX, DCX phase L underscore 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 frequency modulator, A, IIPPM, T, IDT modulator IL underscore 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 II phase modulator, B, relationship between FM and PM from X, 5.3b, and 5.5, it is apparent that PMA and DF not only are ever similar but are inseparable. Replacing M, T, in EQ, 5.3b, with JM, A, de changes PM into FM. Thus, a signal that is an FM wave corresponding to M, T, is al subpm wave corresponding to JM, A, de, Fig.5.2a, similarly a PM wave corresponding to M, T, is the FM wave corresponding to T, Fig.5.2b. Therefore, by looking only at an angle modulated signal LTP, T, there is no way of telling whether it is FMORPM. In fact, it is meaningless toscan angle modulated wave whether it is FM or PM. It is analogous toskinga married man with children whether he's a father or a son. This discussion and Fig. 5.2 also show that we need not separately discuss methods of generation and demodulation of each type of modulation. Equations 5.3b and 5.5 show that in both PMA and DFM the angle of a carrier is varied in proportion to some measure of m, t. In PM it is directly proportional to m, t, whereas in FM it is proportional to the integral of m, t. As shown in Fig. 5.2b, a frequency modulator can be directly used to generate an FM signal, or the message input m, t, can be processed by a filter, differentiator, with transfer function h, s, equals s to generate PM signals. But why should we limit ourselves to these cases? We have an infinite number of possible ways of processing m, t, before FM. If we restrict the choice to a linear operator, the measure of t can be obtained as the output of an invertible linear, time invariant, system with transfer function h, s, or impulse response h, t. The generalized angle modulated carrier LTP-M, T, can be expressed as LTP-M, T, equals A cos V T plus 1 / R, T, equals A cos V T plus F00 M, A, H, T A, D, 5.6a, 5.6b, as long as H, S, is a reversible operation, or invertible, M, T, can be recovered from 1 / R, T, by passing it through a system with transfer function h, s, R1 as shown in Fig. 5.3. Now PM and FM are just two special cases with h, t, equals kp8, t, and h, t, equals k1u, t, respectively. This shows that if we analyze one type of angle modulation, such as FM, we can readily extend those results to another kind. Historically, the angle modulation concept began with FM, and here in this chapter we shall primarily analyze FM with occasional discussion of 206 angle modulation and demodule at ion figure 5.3 generalized phase modulation by means of the filter H, S, and recovery of the inverse filter 1/H, S. Message from the modulated phase through M, T, LL, T, equals FM, A, H, T A, D H, S, 1, H, S, PM. But histo as not mean that FM is superior to their kinds of angle modulation. On the contrary, for most practical signals, PM is superior to FM. Actually, the optimum performance is realized neither by pure PM nor by pure FM but by something in between. Power of an angle modulated wave. Although the instantaneous frequency and phase of an angle modulated wave can vary with time, the amplitude A, PM or FM, is always A remains constant. Hence the power of an angle modulated wave 2/2 regardless of the value of P or T. Example 5. LKT and KP are two NX105 sketch FMA and DPM waves for the modulating signal, T, shown in Fig. 5.4a. The constants and 10n respectively and carrier frequency JSIS 100 MHz. Figure 5.4 FMA and DPM waveforms. M, T, 1-2x10⁴ to -1// plus 1/v, A, V20, 000 ij wii, I/ plus, d, for FM, w, equals we plus ktm, t. M, t, 7r equals 108 plus 51h, t, equals 10.5. 1 nonlinear modulation 207 dividing throughout by 2n. We have the equation in terms of the variable f, frequency in Hertz. The instantaneous frequency f, is f, equals ktfc plus 28 plus 105 m, t, d me n equals 10.8 plus 10.5 m, t, L me n equals 99.9 MHz if I, max equals 108 plus 10.5 m, t, L max equals 100.1 MHz because m, t, increases and decreases linearly with time. The instantaneous frequency increases linearly from 99.9 to 100. Hz over a half cycle and decreases linearly from 100.1 to 99.9 MHz over the remaining half cycle of the modulating signal, Fig 5.4b. PM for m, t, is FM for m, t. This also follows from EQ, 5.3c. For PM, kpf, equals LE plus m, t, 2n if I, men equals 10.8 plus 5.1 h, t, L me n equals 10.8 minus 10.5 equals 99.9 MHz, phi, max equals 10.8 plus 5 m, t, L max equals 100. L Hz because t, switch s back and forth from a value of 20,000 to 20,000. The carrier frequency switch s back and forth from 99.9 to 100.1 Mhz every half cycle of m, t, as shown in Fig. 5.4d. 7R/2 respectively and Fc equals I00 MHz. This indirect method of sketching PM using m, t, to frequency modulate a carrier works as long as t, isocontinuous inal. If t, is discontinuous it means that the P signal acid and phase changes and hence m, t, contains impulses. These indirect method fails at points of that is continuity. In such a case a direct approach should be used at point of discontinuity to specify the sudden phase changes. This is demonstrated in the next example. Sketch FMA and PM waves for the digital modulating signal, t, shown in Fig. 5.5a. The constants t and kp are 2nx105 and example 5.2 III for FM, f, equals fc plus ktm, t, equals 10.8 plus I05 m, t, 2n because t, switches from 1 to 1 and vice versa. The FM wave frequency switches back and forth between 99.9 and 100.1 MHz, as shown in Fig. 5.5b. This scheme of carrier one m, b, d, equals 1 208 angle modulation and demodulation TJI1 dash, a, tm, t, dash dash, dash dash 1 t, underscore 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 comma underscore r, I figure 5.5 FM and PM 99.9 MHz 100.1 MHz, c, I waveforms. 9, FM, I 100 MHz trademark 1111 MMMIU-MMI1 MMMI1 frequency modulation via digital signal, Fig.5.sb, is called because the information digits are transmitted by keying different frequencies, see frequency shift keying sector 7. FSK, 8. 4 PM, underscore, equals FC plus 2 NM, T, KP equals I08 plus 1 4 M, T. The derivative Rie, t, Fig 5.5c, is a rho except at points of discontinuity of m, t, where impulses of strength plus or minus 2 are present. This means that the frequency of the PM signal stays the same except at these isolated points of time. It is not immediately apparent how an instantaneous frequency can be changed by an infinite amount and then change it back to the original frequency in zero time. Let us consider the direct approach. /JPM, t, equals a cos WET plus KPM, t, J a cos WET plus im, t, equals underscore a sin wet when, t, a sin wet when m, t, equals 1. This PM wave is found in Fig called ing the carrier phase. Note that because information digits are transmitted by shift phase shift k'ing, PSK, S.SD. This Shimiov carrier PIM by a digital signal is by M, the T.PM wave of SK may also viewed acids PSK modulation ppm, T, in this case has phase discontinuities at instants where impulses agrees shift in zero time implies infinite instantaneous frequency at these instants. This phase here located. At these instants, the carrier phase shifts by instantaneously. A finite m, t, with our observation about the amount of phase discontinuity in m, t, is kcppm, t, at the instant where Rn, t, is discontinuous. The phase discontinuity in example, the amplitude of PRND where m is the amount of discontinuity in m, t, at that instant. In the present m, t, changes by 2, from 1 to 1, at the discontinuity. Hence, earlier result. ppm, t, iskpmd equals, n/2, x2 equals n. Radwik confirms UR. 5.2 Bandwidth of angle modulated waves 209 where m, t, has a jump discontinuity. We shall know when m, t, is a digital signal, a synfig 0.5.5a, LTPPM, t, shows a phase a discontinuity. Show that to avoid ambiguity in demodulation, in such a case, the phase deviation kpm, t, must be restricted to orange, tc. For example, if Kp were 3tc/2 in the present example, then LTPPM, t, equals a cos wet plus 3, m, t, in this case Cp ambiguity of the receiver when a sin vet is received. Specifically the receiver cannot pm, t, equals as in wet when m, t, equals lor 1/3. This will certainly cause range, tc. Decide the exact value of m, t. Such ambiguity never arises if kpm, t, is restricted with what causes this ambiguity, when m, t, has jump discontinuities. The phase of pm, t, o, changes instantaneously. Because a phase LTPO plus 2 antithesis indistinguishable from the phase LTP, ambiguities will be inherent in the modulator unless phase variations are might to the range, tc. This means should be smally not a restrict the phase change m, t, to the range no such, tc restriction tc, on kp required ifm, t, is continuous. In this case the phase change is not instantaneous, but gradual over time, and a phase percent plus 2 ntc will exhibit an additional carrier cycles. In the case of phase of only followed by an integrator, CPRQ0 we CA and detect the PM wave by using an FM demodulator FM demodula OB 5.41. The additional N cycles will be detected by the handled POTOR and the subsequent integration will yield a phase 2 NTC. Hence CE, the phases percent example 2 NTC can be detected without ambiguity. This conclusion can also be verified from B5. 1. Where the maximum phase change Cp equals LOTC. Cause a band limit signal cannot have jump discontinuities. We can also say that when plus m, t, is band limited,